Okay, one moment here. Okay, so the recording's beginning. Yesterday we talked about section 8.3, and we talked about some different tests regarding series that have positive terms. So we talked about the comparison test, the limit comparison test, and the integral test. In section 8.4, we deal with series where the terms aren't all positive, or they don't have to be all positive. So even the first series here, that series A, you have an alternating series there, an alternating series. So see, when terms of your series are negative, you can't directly apply those tests that you learned in section 8.3. So that's why we have section 8.4. So let me give you a moment here just to copy this example down, okay? And then we'll talk about these examples. Okay, so I'll give you a few more minutes to copy this example, and then we'll talk about these series. All right. Everybody's good so far? Okay. All right. So let's take a look here at this first series. What does that series sort of resemble? The series resembles a series that you've seen before. It's not the same as the series, but it resembles it. Can anybody think of that series? You know, 1, a half, a third, a fourth. What special series does that resemble? Well, it's not a geometric series, right? Okay, that's right, John. It's an arithmetic series. I'm sorry, it's the harmonic series. So the harmonic series, as you know, harmonic is 1 plus a half plus a third, and so forth. Keeps going, right? And we know this series here, the harmonic series, diverges. We know that. Because even though the terms of this harmonic series approach 0, I mean, the series, you know, the series is always getting bigger, right? Because you're at 1 plus a half plus a third. You're always adding positive numbers. So the series gets bigger, but the terms are approaching 0. But the thing is, the terms, even though they're getting smaller and smaller, the rate at which they're getting smaller isn't fast enough to make the series converge. That series diverges. Now, geometric series would, if the common ratio were less than 1, then that would converge, right? Because a geometric series, the terms of the series are they approach 0, but they approach 0 in a geometric fashion quickly, and so that series converges to a finite number. But the harmonic series, this series here, diverges. Now, this series here resembles the harmonic series, but there's a very important difference. What is the important difference with this first series here? It resembles the harmonic series, but there's a very important difference. And what is that important difference? That's right, Robin, alternating. The terms are going positive, negative, and so forth. And this is what's called an alternating harmonic series. It's an alternating series. And because the series is alternating, its behavior is different from a regular harmonic series. This alternating series, we can apply what's called, in section 8.4, we can apply what's called the alternating series test. So let me show you the alternating series test here. We can, let's see here. I have it actually right here. I printed a page out. It's in your ebook, though. It's in your ebook. But this is the alternating series test. If you have an alternating series, and again, an alternating series is where the terms methodically go positive, negative, positive, negative, positive, negative, positive, negative for forever, then if these two conditions are met, the series will converge. The first condition says that the n plus first term is less than the nth term. So that condition just means they're not worried about plus or minus. They're just saying that that if you just focus on the value of the n plus first term, it's smaller than the value of the nth term. So that the terms of the series are getting smaller. The terms of the series are getting smaller. That's what this first condition says, and they're decreasing. It's a decreasing. The terms of the series are decreasing. So for our first series here, 1, a half, a third, a fourth. The terms of the series are decreasing. So therefore, the first condition here in the alternating series test is satisfied. Okay. The second condition is that the terms of the series are approaching zero. The limit of the terms of the series are approaching zero, and that's also true for our particular alternating series. This is enough to make the series converge. So if you want sort of an intuitive feel for this, they have a little picture here where they're looking at different partial sums of the series. And so what they do is they say, okay, well, you know, S is ultimately the sum of the infinite series. That's what I'm interested in. So the S sub 1 is equal to your first partial sum. Well, that's just equal to B1, okay? That's equal to B1 here. And here B1 is of some positive value. So that would be like a 1 for our alternating series. But then when you get to the second partial sum, how do you get there? You take B1 and then you subtract B2. So B1 is positive, B2 is negative, but it's not, in magnitude of B2 is not as large as the magnitude of B1. So B1 minus B2 gets you to the second partial sum. Okay, but that's a little closer to the true sum than was the first partial sum. Now, what's the third partial sum going to be? Third partial sum's here. That's B1 minus B2 and then plus B3. Well, plus B3 makes the third partial sum greater than the second partial sum. So you're over here. Then if you subtract the fourth term from the third partial sum, you're going to end up at the fourth partial sum. And you keep doing this, and what's happening is the partial sums, as you let n go to infinity, you know, here's the fifth partial sum and the sixth partial sum, the partial sums start to congregate around, they start to gather, or I want to say the right word, converge to the true partial sum. That's what's going on when you have an alternating series. So this is intuitively why we can say an alternating series that satisfies conditions 1 and 2 converges. How many find this picture to be helpful in getting an intuitive feel for why an alternating series would converge? Good. Thank you, John. Wonderful, wonderful. So let's then utilize the alternating series test for our problem. We will utilize it because we can't. We have a true alternating series. So in the solution, I mean, if I go back here, okay, what I've done is I've written the formula for this series, okay, and the -1 to the n minus first power is just there so that you can get the plus minus behavior, and you're multiplying that by 1 over n. Well, 1 over n, I don't know, is the same in the alternating series test. That's your b sub n, 1 over n. That's your b sub n. And b sub n is 1 over n. Well, we notice that the n plus first term would be 1 over n plus 1, but that's less than 1 over n. Okay. So the first condition of the alternating series test is satisfied. The second condition is that the limit of b sub n go to 0, and it does. So the second condition is satisfied. And therefore, our series, I'm going to make it so everything shows. The series, this alternating series converges by the alternating series test. Okay, and that's all there is to it. That's all there is to it. A lot of times you can intuitively, I mean, just by looking at the alternating series, these two conditions, the first condition, the fact that the terms of the series are decreasing, and the second condition, the fact that the terms of the series are approaching 0, those conditions you can basically do in your head. You know, looking at the series, you can intuitively see those, if those conditions are satisfied, and then be able to say if the series converges or diverges. And again, you know, for the section 8.4 exercises, those exercises, at least some of them, are ask you, does the series converge or diverge? And you know, you have one chance to get that question right. So you want to take your time before you answer. But you know, alternating series test is a pretty easy test to apply. Okay, are there any questions on that? All right, let me give you a moment just to copy the notes down, and then we'll move on to the second, to part B. Okay, are there any questions before we move on here? Okay, well, let's get to B here. Okay, here we have the series n equals 1 to infinity of -1 to the nth power times 3 to the n over 4n minus 1. Now, we can certainly write out a few terms of this series, right? We can write a few terms of the series. What would the first term be? Is the first term positive or negative? Negative, that's right. That's right. Thank you, Robin. Thank you, Josiah. -1 to the first power is -1. So we're going to get negative what? What's the first term going to be? What's going to be in the numerator? All right, it'll be, let me see here. Hold on, Josiah. 3 in the numerator and 3 in the denominator, and indeed that equals -1. Next term then is positive. This is a strict alternating series. What would the next term be? What's going to be in the numerator? Well, who can actually, I'm just going to ask, what is the next term? I agree, Robin, 6/7. And the next term's negative. And what's third term going to be? That's right. Thank you, Robin. Thank you, Michael. 9/11. Okay, now, and we can keep going. We can keep going. So the terms, well, what are the terms of this series approaching? Are the terms of this series approaching 0? As n gets large, are the terms of this series going to approach 0? That's right, Tyree. No. What are they going to approach? What are they going to approach? The terms of this alternating series. Excellent, Robin. 3/4. And again, you know, what you can do is say, look, when n is large, the -1 really isn't important. And, you know, the -1 to the nth power, I mean, that's going to give the alternating part. But what's going to happen is the terms of the series are going to approach 3/4, -3/4, 3/4, -3/4. That's what's going to happen. 3n over 4n is 3/4. So intuitively, then, well, are there any questions on that before I get to the solution? I'm trying to show you how to. These series sometimes give students difficulty, and if you develop an intuitive feel for the series before answering if the converges or diverges, it'll help you. An intuitive feel is worth a lot. All right, so since the terms of the series they're not approaching 0, right? Terms of the series are approaching 3/4, so the series cannot converge. It has to diverge. And so we're going to use an old friend here. We're going to use the term divergence. So what we do is we look at the terms of the series, and the limit of those terms doesn't exist. Okay, doesn't exist. That's formally what's going on. But intuitively, what's going on is the series, as n gets large, the terms of the series act like 3/4 plus -3/4 plus 3/4 plus -3/4, and so on. The series cannot converge. But students always like, I mean, I understand you want to know by what test is this true. Formally, it's the test for divergence. Test for divergence says that if the terms of the series do not approach 0, the series has to diverge, and that's what's happening. All right, let me give you a moment to copy this solution down before we go to part C. Are there any questions? Thank you, Gabriel. All right, I'll give you a moment here. Julia has a good question. Let me bring up her question. One moment. Okay. Julia, let me get to your question in a minute, okay? I'll get to your, it's an excellent question. Okay, all right. So Julia asks for the future exam, you know, for like your fourth exam, is it enough just to say which test, similarly to what you did as showing our, and well, you do want to apply the test. You do want to apply the test, like I'm doing. I mean, yes. What I see what you're asking, Julia. Do we need to have this part also? Right, this part also, and yeah, formally you do not. Formally you do not. Um, you would not need to have that. You could just uh, apply the test. I might on this next exam, just like I did on the third exam, I might break it into three parts. Two parts being where you show the work, and then the third part might be questions where, you know, does a series converge or diverge? And you know, I wouldn't maybe ask for work. The reason I say that is, for this problem, let's say a student does, you know, this series here, this series. Let's say that a student answers the question where, you know, this series diverges by the test for divergence, okay? And okay, that's correct to answer the question that way. Let's say a student does that. But maybe another student answers the question by saying, hey, Dr. Duty, look, as n gets large, this series behaves approximately like this: 3/4 minus 3/4 plus 3/4 minus 3/4. This series is doing that, so the series can't converge. I consider this intuitive approach shown here with the note, and I consider that intuitive approach to be just as valuable as saying, hey, Dr. Duty, the test, this series diverges by the test for divergence. I mean, both statements show me that you understand this series. Essentially the intuitive approach here, when you say the series behaves approximately, the series behaves approximately like, you know, the terms of the series behave approximately like 3/4 minus 3/4 plus 3/4 minus 3/4, and therefore the series diverges. That to me is essentially saying that shows me that you understand the test for divergence. So what I'm trying to say is, on these series problems where, like in 8.3 and 8.4, those sections where you're asked, does a series converge or diverge? I want to be able to give students flexibility on how they answer that question. And so it may be that for the portion of the exam covering sections 8.3 and 8.4, I might not require, I might just make work optional. I might, that way, you know, or put it this way, if I do require the work, I would give you some flexibility in how you answer the the question. Does that make sense, Julia? Does that help? How many? Okay, you're welcome. How many like having a little flexibility in terms of how they answer these questions? Okay, great. Thank you, John. Thank you, Robin. Wow. Okay, Josiah, getting a thank you, getting a lot of thumbs up on that. Okay, all right. Let us move to the last question here. So now we're on this series here. Does this series converge or diverge? So what I'd like you to do is I'd like you to and make sure your calculator's in radian mode. Compute the cosine of 1 over 1 squared. And is that first term of the series positive or negative? So I don't really need to know the value right now. I just want to know if this first term here, when you put it on your calculator, is it positive or negative? So this is hopefully an easy question. All right, it's positive, okay, and it's going to be positive 0.5403, but I'm not focused on that. That's positive. Thank you, Josiah. All right, now the cosine, next term, cosine of 2 over 2 squared. Is that term positive or negative? Negative. That's right, Robin. Okay, so far it looks like we have an alternating series. Positive, the first term's positive, second term's negative. What do we want the third term to be? We want the third term to be positive, right? So that we can, we have an alternating series. We want to be able to, well, compute the cosine of 3 over 3 squared. Is that positive or negative? That is negative. Thank you, John. Uh-oh. Do we have an alternating series here? We don't. That's right, Robin. We do not. So we cannot use, therefore, the alternating series test to help us with this series, this series equals 1 to infinity of cosine of n over n squared. We can't use the alternating series test. Okay? But what do your instincts tell you? I mean, I guess, we want to think a little bit intuitively here. I have the cosine of n over n squared. The n squared's in the denominator. What series does that remind you of? I mean, that n to some power in the denominator. What type of series does this series maybe remind you of a little bit? That's good. Very good. Very good, Robin. Very good, John. A P series. So is there a way to make a comparison between this series and a P series? Well, you can't make a direct comparison because some of the terms of the series are negative. And the comparison test requires that the terms of, to compare one series to another series, the terms of the series that you're interested in, your series, the terms of the series have to be positive. So the comparison test cannot be directly applied to this series. However, what if we were to consider the series where we had the absolute value of the terms? What if we had the series where n equals 1 to infinity of the absolute value of the cosine of n over n squared? Okay, now that's not our series, but what if we looked at that series and studied if that series converged or diverged? Maybe based on that, we could get an answer for our series. So that's going to be our approach. That's going to be our approach here. So let's get to the solution. Let's be a little bit formal here. So, like I mentioned, since here are I'm just looking at the cosine. The cosine of 1 is positive. Cosine of 2 is negative. Cosine of 3 is negative. And because of this, our series is not an alternating series. It's not. And so we cannot apply the alternating series test. So what we're going to do is we're going to consider this series. Okay, so let me give you a moment to copy that down. Okay. So what we're going to do is we want to somehow get the comparison test involved in this problem, because we have that n squared in the denominator, and that reminds us of the p series. Okay, a p series where p equals 2. So I'm going to consider the series where n equals 1 to infinity of the absolute value of cosine of n over n squared. I'm going to consider that series. And, well, we know that the cosine of n over n squared, the absolute value of the cosine of n over n squared, would always be bounded by 1 over n squared. The reason being is that the cosine of n is always between 1 and negative 1. So it can never, the absolute value of the cosine can never be more than 1. So this is definitely true, this inequality. And notice that the absolute value of the cosine of n over n squared, the terms are always greater than or equal to 0. So we can apply the positive terms. We can apply the comparison test, and we're going to do that. We're going to do that. So since the series where n equals 1 to infinity of 1 over n squared is a convergent p series, because p equals 2, which is greater than 1, this means that the series n equals 1 to infinity of the absolute value of cosine of n over n squared, that would also converge by the comparison test. This series here is larger than the p series. No, I'm sorry. This series here is smaller than the p series by virtue of this inequality, right? So if the P series converges, if its sum is finite, then our smaller series here would also have to converge. By the comparison test. All right. Give you a moment to copy that. All right, are there any questions so far? We're not done with the problem yet. We're not done with the problem yet. All right, so the fact that the sum, where n equals 1 to infinity of the absolute value of cosine n over n squared, the fact that that converges means that we say that our series converges absolutely. This means that our series is this is the series where n equals 1 to infinity of the cosine of n over n squared, without the absolute value. That's the series we're interested in. We can say that our series is absolutely convergent because the series where you take the absolute value of the terms of the series, that series converges. So our series is absolutely convergent, and therefore if our series is absolutely convergent, it must be convergent. The idea, all right, let me let you copy that down and I'll make a comment on that. Okay, I'm writing something down here. I want to give you a feel for why this is true. Okay, and I'll show you why. I want to show you why the fact that if the series converges absolutely, the fact that it converges, why is that true? And I'm going to give you a feel for this. Okay, so what I've done is at the bottom here, I have two series, the same series, but there's a negative in front of the series on the left, and the right series, there's a positive there. and a big space in the middle, and I'll fill in that big space in the middle. But the series to the right is the series to the right finite or infinite? This series to the right. Is the sum finite or infinite? Think about this. Think about, so I'm glad I'm asking this, because think about that statement there. We proved this. So would this sum here, the sum of the cosine of n over the sum of the absolute value of cosine of n over n squared, would that sum be finite or infinite? It has to be finite, of course. That converges, okay? So that's finite. Okay, thank you, Robin. That's finite. Now, what about this series to the left, which is the same series, only there's a negative in front of the series? I mean, we didn't involve that, but I'm just asking, would this series to the left also be finite? Yes or no? Absolutely. That's right. It has to be finite. I mean, it's just the series on the right is some number, equals some number. The series on the left is going to be negative of that number. So this is going to be finite as well. Okay. All right. Well, now let me write here. Let me write our series right in the middle here. Cosine of n over n squared. What can we say about our series relative to these two outer series? Our series, its sum is, there's a word I'm looking for. Our series, its sum is blank relative to the relative to this series and this series. Our series would have to be blank relative to those two series. If the word begins with a B, that's right, Robin, between. Very good. Our series has to be less than the series on the right and greater than the series on the left. Okay, so I mean that has to be true because the terms of our series, some are positive, some are negative. So that series would have to be less than the series on the right, but it would have to be then greater than the series on the left because, you know, the series on the, well, yeah, it would have to be greater. And so the fact that our series is between two finite series, the sum of our series has to be between the sum of these two of these two finite series. That means our series then would have to be finite also. Has no choice. And so this is the idea behind using absolute convergence to determine if a series is finite or not. Okay, is this helpful? This little intuitive discussion here. How many found that to be helpful? Thank you, John. Thank you, Robin. Is anybody uncomfortable with that? It might take some time. You might have to replay the video again to get a comfortable feel. But the idea, really the idea is, another way to think about it is, when you have a series where you look at a series and you take the absolute value of the terms of the series, and that series converges. Well, the series where you take the absolute value of the terms, that has a better chance of diverging than the series when you don't take the absolute value of the terms. So if the series where you took the absolute value of the terms converges, because that series, all the terms are positive, so but if the series where you took the absolute value of the terms, that series converges, then the series where you don't have the absolute value of the terms, that series would also have to converge. I mean, it would have to, because this series here, right, is certainly greater than the series we're interested in, and so yeah. But okay, is that helpful? Are we okay? Who at least has a little bit comfortable with this? Okay, thank you, Tyreek and John, Josiah. Good. So it takes a little time. All right, well, let's move to the next example. Let's look at two more series here. We want to determine whether these series converge or diverge. I'll give you a moment to copy them down. Okay, so we want to determine if the following series converge or diverge. And let's look at the first series. So the first series here, n equals 1 to the series where n equals 1 to infinity of sine of 4n over 4 to the nth power. We're not going to, that's not an alternating series. Now the second series is the second series here, where n equals 1 to infinity of negative 1 to the nth power times n cubed over 3 to the nth. That is an alternating series, because you have the negative 1 to the nth power there, and that's going to, as n goes through its values, negative 1 to the nth is going to be, negative, positive, and so forth. But the first series is not a true alternating, it's not an alternating series. I do see here a, 1 over 4 to the nth power. I see a 4 to the nth power in the denominator. What is that? What series does that remind you of? What does that remind you of, having a 4 to the nth power in the denominator? That reminds me of a series that we've discussed before. Essentially what I'm doing, okay, that's right, Josiah, geometric series. It reminds me of a geometric series. So what if I could relate this series to a geometric series? What if I were to use the comparison test? Well, I can't relate the series directly because the comparison test is only used for series with positive terms. So what we have to do is consider first the series where we take the absolute value of the terms. So on that note, we will do that. We will do that. Okay, so we're going to be looking, hold on, clear that. We're going to be thinking about this series here. Let's think about that series. The sum where you have the absolute value of the sine of 4n over 4 to the nth power. Well, the absolute value of the sine of 4n over 4 to the nth power would be less than or equal to 1 over 4 to the nth power. Because the sine of any angle always is between -1 and 1. So the term of this series is less than 1 over 4 to the nth, but that then can be written as 1 over 4 to the nth power. And so I look at the series. N equals 1 to infinity, n equals 1 to infinity, of 1/4 to the nth power. I write out some terms, and clearly it's a geometric series. What's the common ratio, by the way, for this geometric series? It's convergent. Why? Why is that geometric series convergent? Well, what's the common ratio? That's right, John, 1/4. So the common ratio is 1/4. It's a little bit big, sorry. And that's less than 1, right? So therefore, it is a convergent geometric series. And there's a formula to get the sum of that convergent geometric series, but I'm not interested in that right now. Okay. The fact that I do have a convergent geometric series means then by the comparison test, the series n equals 1 to infinity of the absolute value of sine of 4n over 4 to the nth power, that must converge because it's a smaller series by virtue of the inequality here. It's a smaller series than our convergent geometric series. Well, that's good news. That's good news because then we can say that our series converges absolutely and therefore converges. Done. Easy. Okay. All right, take a moment to copy that down. Okay. Are there any questions at all on this? Are there any questions on this problem? Okay. All right. Well, let's go to that second problem. Here we have the series where n equals 1 to infinity of -1 to the nth power over n cubed. The series goes n equals 1 to infinity of -1 to the nth power times n cubed over 3 to the nth power. How many feel that series looks kind of complicated? It's an alternating series, but how many feel that that series seems a little more complicated than the other series that we looked at? Well, it's an alternating series, right? It's an alternating series, but could we use the alternating series test on that? To use the alternating series test for this, the reason I mention it is normally students see this and they say, oh, that's an alternating series. I'm going to use the alternating series test on that. But to use the alternating series test, you have to satisfy the two conditions. Okay? The two conditions being if we go back here to when you learned about the alternating series test, you have to show that the terms of the series are decreasing, and then you have to show that the terms of the series are approaching 0. Okay, now for the series that we had We were able to show this quite easily for that alternating harmonic series example. But for this problem here, for B, okay, B sub n is equal to n cubed over 3 to the nth power. Okay. And like, let's just consider showing the limit of this term. Could we show the limit? Well, I want to be a little careful here. The thing is, it probably would, I could probably show that, I mean, taking the limit as n goes to infinity of this nth term, we would use L'Hopital's rule. And maybe we could show that I want to be careful how I state this. We could likely show that terms of the series approach 0. However, showing that the terms of the series are decreasing is another matter. It's not easy to apply the alternating series test to this second series because it's what I would call a complicated series. I'm not going to apply the alternating series test to a problem unless it's easy to use. And the comparison test is not going to be so easy to use here either. Like if we wanted to consider absolute convergence, the n cubed over 3 to the nth power, what would I compare that to? If I had like 1 over 3 to the nth power instead of n cubed over 3 to the nth power, I could compare that to a geometric series quite easily. But you have in here, you have an n cubed in the numerator. That makes it complicated to just directly compare this to a geometric series. So what we need is, we need a new test. And the test that we're going to use, whoops, hold on here, I think I went past. Test we're going to use is called the ratio test. Okay, let's talk about the ratio test. So this is in your ebook, but I have it here as well. So you have a series. And the terms of the series are denoted a sub n. If the limit of the n plus first term divided by the previous term is equal to L, and that's less than 1, we say the series is absolutely convergent, and therefore convergence. Because what we're doing is we're considering the absolute value of the terms of the series. We're taking this limit here of that ratio is the same as the limit of the ratio of the absolute value of those terms, right? This is equivalent. So essentially, you're trying to establish convergence or divergence of this series here, where you have the absolute value of the terms. And if that series converges, we would say the series then, that our series is absolutely convergent. And you just learned that. But in this ratio test, it's sort of interesting because they're studying the ratio of the n plus first term over the nth term, And they're saying, look, if the limit of that ratio, as you go out in the series, if the terms of the series are such that a term divided by its previous term is equal to L, or approximately, the limit of the, I want to say this the right way, as you move out into the series, as you go out into the series, if for n large, if the ratio of two consecutive terms equals L, and L is less than 1, then our series absolutely converges. So first of all, L reminds me of something, and 1 reminds me of something. Okay, L reminds me of something, and 1 reminds me of something. What does L remind you of? When you're taking a term of a series and dividing it by the previous term, you're computing a what? The word I'm looking for begins with an R. That's right, Robin. You're computing a ratio. This L is excellent. This L is a ratio. And if the ratio is less than 1, under what the series converges absolutely? What series is such that if the ratio is less than 1, the series converges? What series behaves like that? If the absolute value of the ratio is less than 1, this series, or I should say this, if the absolute value of the common ratio of the terms of this series is less than 1, this series converges. What's the series that does that? I'll give you a little hint here. What series does that? I think I gave too big of a hint, but if somebody could chat it out, I'd appreciate it. Geometric. Thank you, Josiah. So what you're really doing is you're saying that if the terms of the series, if as you go out into the series, as n gets large, and remember, convergence or divergence of a series depends on convergence or divergence of a series is dependent on the eventual behavior of the series. So what this first statement is saying is, if you look at the eventual behavior of the series, and a term in the series eventually a term in the series divided by the previous term in the series, if that ratio converges to a constant L, which is less, if that ratio converges to a constant L, you're saying that your series eventually behaves like a geometric series. You're saying that your series eventually behaves like a geometric series. Because a geometric series, the ratio of two terms is always equal to a number, right? That it equals that common ratio. Well, what you're saying is this: if this condition here is satisfied, and I'm underlining it in red, if that condition is satisfied, you're saying eventually the terms of your series behave like a geometric series, because the limit of the ratio of the terms of the series is going to equal a constant, and that is that is the behavior of a geometric series. Now, if your series behaves like a geometric series, and the ratio of the terms is approaching a limit L that's less than 1, then your series has to converge. However, in part 2 here, if that limit of that ratio converges to a number L which is greater than 1, the series has to diverge, because geometric series with common ratios greater than 1 diverge. Now, also, if the common ratio, if your series, if the limit of the ratio of the terms of your series approaches 1, then the ratio test is inconclusive. Geometric series converge if the absolute value of the common ratio is less than 1. Geometric series diverge if the absolute value of the common ratio is greater than 1. But there's no statement at all if the common ratio equals 1. Okay, so in that case, the ratio test is inclusive, and if that were to happen, you'd have to try to find another test. So what we're going to do with our complicated series is we're going to apply the ratio test. And I want to do that, but are there any general questions on this so far? Okay, let's apply that ratio test. Let's apply it. So for our series, none of the previous tests we learned can be easily used to establish convergence or divergence of the series. Okay, so therefore, let's try the ratio test. Okay, and I'm gonna stop and let you copy, but I'm gonna just show you the first step here. So the nth term of our series is -1 to the nth power times n cubed over 3 to the nth. So that's a sub n in the denominator here. But then in the numerator, you have the n plus first term. The n plus first term comes by just replacing everywhere you see an n in the term, replace it with an n plus 1. And then you're going to take the absolute value of this ratio. All right, let me stop there, let you copy this down. All right. Are there any questions so far up to that step there. All right, so what we have to do now is we have to do some math on this to figure out what this ratio is. So I have a fraction divided by a fraction, and you've been taught when you have a fraction divided by a fraction, you take the top fraction, right, and multiply by the reciprocal of the bottom fraction. The top fraction divided by the reciprocal of the bottom fraction. So if we do that, that's not hard. I'll just rewrite my ratio this way. And so I have to do a little simplifying here. I have to do a little simplifying, but are there any questions getting to this step here? All right. Well, what I'm going to do is group terms together. I have a -1 to the n plus first power in here, and let me just use the marker here. Here I have a -1 to the n plus 1 power, and here I have a -1 to the nth power. It makes sense to rewrite the fraction having those expressions over each other. Okay. Similarly, I have a 3 to the nth here, 3 to the nth power there, and a 3 to the n plus 3 to the n plus first power there. It makes sense to, write them over each other, right? And then the n plus 1 cubed and n cubed, I put those over each other. It just makes sense to do that. Okay. So -1 to the n plus first power over -1 to the nth power, what would that equal? What does that equal? The base is -1. What do you do with the exponents? Subtract them. That's right, Josiah. So, all right, that means n plus 1 minus n equals 1. And so this is going to equal -1. Well, it's -1 to the first power, right? But that's just -1. Okay, what's 3 to the nth power divided by 3 to the n plus first power? What's that equal to? So well, that's right, Josiah, 3. Remember, that's right, very good. You do subtract the exponents. Remember, 3 to the n plus first power, you can write as 3 to the nth times 3 to the first. If you want, you can do it this way. 3 to the n plus first power is 3 to the nth times 3 to the first. Add the exponents, you get n plus 1. So the 3 to the n's drop out, and you're left with 1/3. How many like thinking about it like that? instead of subtracting the exponents. Okay, all right, well, great, all right. All right, well then, so now I want to move to the next page. Are we good so far? Okay, well, let's continue then. Let's continue. So our ratio, simplified, is going to equal the absolute value of -1 to the first times 1/3 times n plus 1 over n cubed. But the -1 and the third come out as a third. Okay. And I can write n plus 1 over n cubed as 1 plus 1 over n cubed. And then I take the limit. So let me let you copy that down, and let's make sure we're all comfortable up to this step here. Okay, so n plus 1 over n cubed is the same as 1 plus 1 over n cubed, and I wrote it that way so that, you know, as n gets large, remember, you're letting the limit, you're letting n go to infinity, right? You're letting n go to infinity. So that 1 over n is going to go to 0. And so this is going to approach, this is another way of writing a limit. You can use an arrow. The ratio approaches 1/3 times 1 cubed, which equals a third, which is the limit L, which is less than 1 as n goes to infinity. Okay. Okay, that's true, right? So what's that tell us? What's that tell you then? What does the ratio test tell us then about our series? Does our series converge or diverge? What must it do? The ratio of the terms as n gets large approaches a common ratio, 1/3, which is less than 1. And that's right, Robin and Michael, thank you. It's going to converge. And therefore, our series is absolutely convergent and hence convergent. Okay, are there any questions on that? Any questions on that? Now, if we had gotten a common ratio that were greater than 1, we would say this series diverges. Okay, so Are there any questions on the ratio test? I might make a few more comments on this problem, but I'll mention traditionally what happens is after students learn the ratio test, they tend to want to use it like all the time because it's a very kind of very structured procedure. You just take the absolute value of the ratio of the terms and study the limit as n gets large. But a lot of times, if you just do that, you'll find that the absolute value of the common ratio will equal 1. What I mean is the limit of the ratio will equal 1, and then the ratio test is inconclusive. So like for some of the easier problems that we did today, you might apply the ratio test and you'll get inconclusive results, meaning the ratio would approach 1, and therefore the ratio test is inconclusive, and so you'd have to solve those problems perhaps like the way we did. So don't think the ratio test can be used all the time. A lot of times it cannot. But for a complicated series, usually the ratio test is the way to go. If it's not obvious what comparison you would make if you use the comparison test, if it's not if it's a complicated alternating series, usually the ratio test is good. Now I'll make one more comment here about this problem. These are just some final intuitive notes that I think are helpful. So we note the later terms of the series, okay, where we take the absolute value of the terms, will behave like a convergent geometric series with common ratio a third. So eventually the series where we take the absolute value of the terms, that's going to act like a convergent geometric series with common ratio 1/3. That's what's going on. And so then if the series with the absolute value of the terms converges, then surely our series would converge as well. That's intuitively what's going on here. Let me give you a moment to copy that, a couple moments. Okay. All right. So, are there any general questions on this? So I know it takes a little time to copy the little notes that I make, but is this note, how many of you find this intuitively helpful for what's going on with the ratio test? Thank you, John. Great, great. Okay, so this is the last example I'm doing today. Even though the document has another example, I'm going to stop there. Let me stop the recording.